denominator, you will get these values equivalent to these values. Any doubts so far, any one of you? Generally, this term we are only going to use in the derivation. We are going to use this in the deviation form. X minus x bar is, we can just small xi, this is the deviation form, and deviation form for y, and deviation form y for the this denominator. So if you still have this doubt, then now you can ask. So these are the two parameters that we have estimated. Beta, this is a intercept coefficient and slope coefficient. These are the values we have now for these with the OLS method. So this is how with the OLS we estimate these two parameters. So these regression lines, which we have these values here, this slope coefficient and the intercept coefficient, these values are actually by these methods, this OLS method. Behind the estimation of parameter. What, Gagan? Actually, earlier I have these derivations, my own derivations in the, I sort out it while I was in the masters, and then later on I improved in last 2 years. But from the last 2 years, I'm traveling from place to another, and recently I found that my whole total this packet of this all the derivation where I kept it separately, and now I have lost it. So I have to do it again from the very beginning, and it's very time consuming thing. So, but still, the maximum time, whenever you have any doubt, I'll try to sort it out with these derivations. So this is something important as a theoretical framework, that how this Stata is calculating these values. It's not that again and again you are going to use it, just to get an idea, give you some idea that how these values are, means from which method and why this method we are going to use. Is it behind the estimation of mathematical equation? Which equation, Gagan? Okay, anyone have any doubt in this derivation? Means so far in this derivation, just used summation property. The summation property of constant and constant with the variable, and only this part from the mathematics, chain rule and minimum property, because we but we want minimum value of this summation U hat square. So anyone of you have any doubt? This is how we derivate regression coefficients with OLS methods. The important part is the assumptions here, that there are assumptions. It's not that you can just directly apply this method. There are few assumptions regarding your sample regression function or equation. If those assumptions will fulfill, then only we can apply this particular method of minimizing summation U hat square. And if with the derivation, this last values which we are getting is with the OLS method, this we can only apply when all the assumptions will be fulfilled. So tomorrow I'll take these assumptions in detail one by one, because those are very crucial, and 3 or 4 assumptions we are going to study in detail, that multicollinearity problem, heterostaticity, and rotation. That's important part. But actually, if you have anyone of you have doubt in the derivation, you can just go through the textbooks. These derivations you can easily find. Okay, so with that, one other thing which I want to highlight today is that the importance of this stochastic disturbance term, this error term or the residual term. Just this, now you can now realize that this whole derivation of the OLS method of the this sample estimates is with the something we are minimizing, that's with the U hat, means the residual part. This is very crucial in the econometric. What is the role of the stochastic disturbance term, and Indirectly, I can say we are estimating based upon its value, U hat value, not the actual values, but uh, this is theoretical. The actual thing is that first we estimate the parameters and then we in the sample, and then if we subtract y hat from the y, then only we can get u hat. But while we're doing a derivation, this is I hope you are getting this point, that while we are doing the derivation, then first what we have, u hat in the upper hand corner, and we are minimizing it, means we are estimating beta 1 and beta 2 in such a manner that we are minimizing this summation u hat square. But in practicality, means in this data, in the practical, while you're going to do this exercise, this u hat value you will get in the end. First, you have to estimate the parameter, then predict the y hat, then y minus y hat, that's the estimated values. That's our error residual term, u hat. So this will come in the end. First you have a parameters, then you put the parameters value, and then you estimate this y hat, then y minus y hat, you will get u hat. Because you don't have any u hat values or unknown parameters values, that you will only get in the end. But while we do the derivation part, we start with the u hat, means it's in the first that we are going to minimize this particular. So this is theoretically it's derivation that you can keep it in the first, but it's not that practically we can do it, because unless and until we can estimate these sample estimates, beta 1 hat and beta 2 hat, we don't have any u hat value, right? So theoretically it is possible that you can do this derivation, but practically u hat value only come after the this estimation of these parameters. So this is the tricks, means this is the tricks here in the derivations and all that, how they are giving us these solutions. So this is something which I found interesting these tricks. It's not that you have to cram these tricks, just by practice you can understand. But in practical field, it's not important that you learn the derivation or not. But yes, the at least you have to some idea. You have some idea that how these derivations are done, how these values are coming. Because in the end, you are going to interpret and you are going to write your results based upon these estimates, right? So it is important that you can understand the process behind these values, all these values which you're going to interpret, and based upon that, you are going to take a decision making process. That's only purpose I'm trying to do some derivation part here. Otherwise, in the applied part, means it's not that we are going to derive anything derivations and then only software automatically calculate these values. But to understanding, it's important that you know how this method is working. What is the background picture in this particular method? That I hope that's important that you can get some idea about that. So this is OLS estimator. And Gagan is asking, is there need to use this derivation process while applying model, or it will work behind the estimation? Gagan, it will work in the software. Software derivation you are not required. They already put these functions in the software so that you can get these answers. Now, here in this particular stochastic disturbance, this array term, its importance is that first, let's suppose you don't know unknown factors, like, yeah, let's suppose yesterday we were taking these values for wage and education model, that wage is not only depend upon the education, there are other factors as well. So those factors, with the array term, you have now space in the regression. You can put those all unknown factors in the array term with the residual. Means this array term can capture all this, so it is helping you. Second, suppose you know the variables, but data availability is not there. Then also this array term is, because for all other things, array term is there. Core variables versus peripheral variables. Like, for example, there might be other variables which are not so much important, or if I can talk in the form of proxy variables, like this permanent income hypothesis. and the consumption hypothesis. That is permanent income and permanent consumption, but that's not easy to capture. So in place of that, we use income and consumption. Those are the proxy variables. Means even in that case, this array term will help us. Then in the core and peripheral elements, if let's suppose you have some peripheral other important variables, but that's not you want to work upon, or that's not so much important. So like in the Keynesian psychological law of consumption, the rate of interest is not there in the consumption function, although many monetary economists say that this rate of interest is also important in the consumption behaviors, but that's not there. So you can put all those factors in the array term as residual. Then intrinsic randomness in human behavior. It's not always for that. You can, even if you know all the variables, you can capture all the data sets. But this is human nature that it randomly it change. So that change you can't capture with the variables you have in the model. So again, array term is helping you. The proxy example I already giving you that the for permanent income and that permanent income hypothesis, permanent income and consumption variable is not possible to calculate. So in place of that, we use proxy variables. Then let's suppose you have some wrong functional forms. It's quadratic type of curve. It's required, but in place of that, you use the linear functional form. Then that remaining part, this array term will capture. So this array term is means like a box you have, some box you have, where you can put all other things which you think are not necessary. So this is importance of this array term. And this all derivation of OLS is around the array term. Means we are going to minimize this. Okay, sorry, the light is not here. So when the sir is asking, we have to write y hat or over dependent variable, then to predict it. So the y hat only if when we are estimating means this is the estimated values, like in this softwares while we work, y hat is only the estimated values, but if the actual values are not the y hat values, mean this actual value is that is yi, that's not the estimated value. Estimated part is only this one, beta 1 hat plus beta 2 hat xi. So this one is only the y hat, but with that we have also the unknown variables, that's the u hat is there, always there. So yes, if you're saying typing in the estimated form, like while you're writing it in the research paper, this particular model, you are not going to write the UI because you don't know these values. That's what I'm saying. While we do these derivations, we start with the u hat scale, but The actual process is that first we have to estimate these parameters in the softwares, and then only we have these estimated y hat values. So for the y hat values, this is only estimated value. So just to differentiate it with the actual value, we use this notation. I hope I answered it. We have to write y hat or over dependent variable then hat. Yes, sir. For estimation, it's into y hat. Like in the graph, this part is only the estimated line part. Other actual values are the actual values. So for this notation, we give this particular space. Any other doubt in this particular? Means here, this is the only estimated part, and gap from actual value is estimated gap that we try to minimize. But yes, this is theoretically, I'm saying that always keep in this mind that when we do this derivation, this derivation is totally theoretical. Theoretically means we are saying we have to minimize this gap between actual values and estimated values, and that gap is your u hat. But you don't have a u hat values unless you have the estimated sample estimates like beta 1 hat and beta 2 hat. Then only you can calculate the u hat. But theoretically, you can say that we are going to minimize, so we keep it equal to 0 and we estimate the formulas for beta hat, beta 2 hat. And these formulas we can use to estimate the parameters with the OLS method, because we are proving here that with this method, we are proving that the value, this is the only possible value of summation u hat square. The other technique we use MLE, that's totally different. Means that's not that we are trying to minimize it. No, that's totally a maximum likelihood function, which I'll take in the last if we have some extra class. Means then I'll take in this part 3. Otherwise, in the part 4, that's totally different approach. Here we are minimizing, and the MLE we are trying to maximize. But that maximize is not the U hat. That's different. So for today, I'm not going to that detail. What is the Y variant of our data? Wage. In this regression example, dependent variable is your y variable. This is something the graphical form that we generally formulate, and these softwares are designed such a manner that they take y as a dependent variable and x as independent variable. But there is no something that hard and fixed rule. Like if you study public finance with the Musgrave and Musgrave, he always his axis is totally different. Means his axis is on the y-axis and y is on the x-axis. So their diagrams are totally different. So this is about the derivation of sample estimates beta 1 hat and beta 2 hat with OLS method. So this derivation you have to practice. If you want to become master in these derivations, then practice is required. And it's not the only one way. Means you can, if you go by different books, they use different tricks, but in the end they prove that this particular value is equivalent to these values. And because few other proofs are required of the properties, that's why this particular type of formulas they are using deliberately, but you can use any of them. Okay, so this was about the derivation. If you have any doubt, then please, because if anyone of you are doing it first time, in the derivation you might face difficulty, but you have to try it. Means these basic derivations are in the internet. Means there are many other available